section 4.6 in Anton is about the change of bases. And we're going to need this in chapter 5 when we change from one basis to another, sometimes to an easier basis for that particular problem. Okay, so things are a little bit complicated because there's just a lot of things and indices and letters floating around, and we've got two bases, not just one. So here I've drawn somewhat a schematic picture of what's going on. We start with a vector space V, and if we choose one basis, B, it consists of some vectors v1, v2, all the way up to vn, and then by definition of a basis, any vector in our vector space V is a linear combination c1, v1 plus so on, cn, vn. And so to V, we can associate this these n numbers, n real numbers, c1 up to cn, called the coordinates of the vector V relative to the basis B. And that notation then is bracket V subscript B to denote the column vector out of these that consists of these numbers. For example, if the numbers are 1, 0, 0, 0, 0, then C1 is 1, the rest are 0, so our vector V is just V1. 1 times V1 plus 0 times everything else is 0, so we're just left with V1. Okay, now suppose we had a different basis, B primed, consisting of some other n vectors, V1 primed up to Vn primed. Then an arbitrary vector V, here in magenta, can be written as some linear combination of the vectors V1 primed up to Vn primed, and we're calling that linear combination C1 primed, V1 primed, plus so on up to Cn primed, Vn primed. And so the coordinates of V in this new basis B primed is given by these numbers C1 primed up to Cn primed. And these are in general going to be different than the C1 and Cn here. Now let's look what happens to V1. Well, V1 is some linear combination, which we don't know exactly, of the V1 primes all the way up to Vn primes. Again, that's because a basis, by definition of a basis, every vector, in particular V1, can be written as a linear combination of the basis vectors. Okay, so V1 has coordinates given by this column matrix, again for these some numbers a1 up to an. And then what we want to do in this section is find how to go from the coordinates of a vector in the basis B, so these numbers, what do we do to these numbers to get the coordinates of that vector V in this basis? How do we get these numbers? And it turns out that there's a matrix. You multiply on the left by a matrix called the change of basis matrix from B to B primed. So B is your old basis, B primed is your new basis, and the way it works is if you give me the coordinates in the old basis, so that's this column vector here, I take this matrix. This matrix does not depend on V, the vector. It only depends on the two bases. So no matter what vector you give me, it's the same for this change of basis matrix, just is the same. It only depends on the two bases B and B prime. Okay, so then the new coordinates of the new coordinates of V, the same vector V, are given by, you take your change of basis matrix and then multiply by the old coordinates, the coordinates of V in the old basis B. Now the question we're going to ask and answer in this video is how to find this matrix. What are the entries of this matrix? Well, we've kind of seen what the first column is going to be, because the thing to remember is when you multiply a matrix by this particular matrix E, the 1, 0, 0, 0, that's the standard basis vector, you extract the first column and of the matrix. And so therefore, this thing here, which is expressing v1, the first vector in our basis, is going to, in expressing the first vector in our basis as the linear combination of the new basis, that's going to be the first column of this matrix P that we're trying to find. So let B primed, with brackets around it, be the matrix formed by throwing the vectors forming B primed into a matrix as columns. So these tick marks here are not ones, but they just indicate the matrix Vi primed as column vectors. And then what we were saying on the last slide is that the first column of this matrix is given by expressing V1 as a linear combination of the vectors making up B primed. And we've seen a few videos ago that that corresponds to multiplying this matrix made up of columns of the basis by the coefficients. And here I've just written it in a different way, moved the V1 over to this side. And so we're trying to solve for A1, 1, AN1. Here I've now indicated this extra subscript 1. Previously that was missing on the previous page. You'll see why in a second. But anyway, B primed times this unknown column vector is equal to this column vector V1, which we are assuming is given. So we're assuming V1 is given, and V1 prime, V2 prime, and so on, Vn prime are given. So these two basis vectors, these two bases, B and B primed, are given. And we're trying to find out what P has to be. And this is the first column of P. And again, the reason is we want to express V1. Again, the reason for why this equation holds is we want to express V1, the old basis vector, as a linear combination of the vectors in the new basis. And so then solving this equation for this unknown here, we can do that by multiplying both sides of the equation by the inverse of B primed. That's going to be an invertible matrix because B primed, it consists of a basis. So then we get that this unknown is equal to B primed inverse times the column vector V1. And there's nothing special about V1. And in general, the ith column of this is going to be given by take the inverse matrix of B primed and multiply that by V sub I. So here's a way to compute this change of basis matrix P of B to B primed. So form the matrix B primed followed by B. You can leave this vertical sign off if you want. So this is going to be an n by 2n matrix because each of these matrices B prime and B is an n by n. So this new matrix, this augmented matrix, in some sense has n rows still, and 2n columns. This has n columns and this has n columns. Okay, and then all we have to do is row reduce this matrix, and then when we do that, there will be an identity matrix in the first n rows and columns, and then what's left over here will be the change of basis matrix. So that's it, that's the procedure. You form the augmented matrix new basis, expresses the column vectors, and followed by old basis, then just row reduce. And we'll do an example on the next slide, but let me just say a few things that will be helpful to remember. So first of all, why does this work? Well, think about how we would solve, even in chapter 1, this equation B primed times some unknown is equal to V sub j. That's the equation we were trying to figure out earlier. What we would do is we would form the augmented matrix B primed and then Vj, and then row reduce it. And so that's exactly what we're doing here, except we're just throwing all these columns making up B into one big matrix B. Remember, the Vj is the jth column of B. Okay, one convenient fact that will be helpful in the example that we work is that if the basis you start off with is the standard basis, in which case the associated matrix is the identity matrix, then the change of basis matrix from the standard basis to some new basis B primed is given by taking B primed, putting into a matrix, and taking the inverse of that matrix. Why is that? Well, remember that was the procedure of how we found the inverse of a matrix. If this matrix B is just the identity matrix, then when we take B primed and the identity matrix and row reduce it, way back I think in chapter 1, we saw that we would get the inverse of B primed here. You can also argue by looking at this column would be EJ, and then you're trying to find some columns that when you multiply by B primed, you get the identity matrix, the n by n identity matrix. And so that's how these columns form the columns of B primed inverse. Okay, so now finally let's look at the schematic diagram of kind of what we began the lecture with. We are trying to compute this matrix here, this change of basis matrix from B to B primed. Then what we do is, well, we can go from here to here by a matrix multiplication, but what we can also do is, well, recall that this point here says that to go from the standard basis to the basis B, you do multiplication by the inverse. So we do multiplication by B inverse to go from here to here. So that means to go from B to S, we multiply by B, and then from S to B primed, we multiply by B primed inverse. That's again this point here. And so the composite here is first multiply your coordinates by B, and then multiply by B primed inverse. And so another formula which we'll check in Sage is that the change of basis matrix is given by B prime inverse multiplied by B. In this picture, we do B first and then B prime inverse. Here I've switched the order because matrix multiplication is, we're multiplying by the coefficients or coordinates here. And so that's why we want to multiply the coordinates of a vector in here first by B, and then that will land us in here, and then by B prime, that will land us in here. Okay, so all of that was fairly abstract. Let's do a concrete example. I'm just going to hurry things up, do things in Sage instead of doing all the algebra arithmetic really by hand. So, okay, so this is number 3, and it says, consider these two bases, B and B primed, where the vectors making up B are given by so, and vectors given by B primed are given by so. So these are two bases of R3. And here I've just formed the matrix B in Sage. So the notation or the syntax is rational coefficients, that's QQ. It's a 3 by 3 matrix, and I enter the rows first. So 2, 2, 1. That's where I get these numbers. Then 1, -1, 2. And then finally 1, 1, 1. Okay, so that's the matrix B. B primed. Now here I wrote out B primed. If I put B tick mark, that will make Sage or Python think that I'm trying to define a string, so that'll give me an error. So I can't use the tick mark here on B primed. So I just wrote out B primed, something like this. Okay, so similarly we enter B primed and we get this matrix. Okay, and then now I'm going to form the augmented matrix through this command here. So I take B primed and augment the matrix B to have this vertical line, which is not totally necessary, but it looks nice. Add the optional attribute or argument, subdivide is equal to true. And so that just gives, this puts in this line, subdividing. Here's the matrix B primed, and here's the matrix B. Okay, so part A of the question says, find the transition matrix from B to B primed. And what we learned on the previous slide is the shortcut, or the way to do it is all you have to do is form this augmented matrix and row reduce it. So the command for that is RRF, stands for reduce row echelon form. So then we get the identity matrix and then this matrix here. And that's exactly the answer, this matrix here. And to extract it out of this is a 3 by 6 matrix. If we just want to recover that, the notation to do that in Sage is brackets, and then this first colon says that you don't care about the rows. The rows can be all rows or will be all rows. Then 3 to 6 refers we want rows 3 to 5. It's a funny way how Python numbers things and what intervals in Python refer to. So the numbering column starts at 0. So this is column 0, 1, 2, 3. So this is the first column we want to capture. And so this is 3, 0, 1, 2, 3, 4, 5. We want to end at column 5. And if you want to end at column 5, you have to put one more, 6 here. That's a little strange quirk of Python, but okay. So anyways, now this is our matrix P, and this is the answer. And to compare with the other way you can find P is to do B prime inverse and multiply by B, and we get the same answer. Part B of the problem says, let S be the standard basis and let W be given by, as a column vector, -5, 8, -5. So these are the coordinates in the standard basis. Find the change of basis from the standard basis to B, and then find the coordinates of W in the basis B. So the solution is, well, we've seen that the change of basis from the standard basis to the basis B is given by the matrix associated to B inverse. And so therefore, the coordinates of W in or relative to B are given by B inverse times W. And so that's the answer. And let's check that in Sage. So I made this matrix W as a 3 by 1 column vector. And then to find the coordinates of W relative to the basis B, I type B dot inverse, parentheses, and then multiply that vector. So that will compute B inverse, and then multiply that answer by W. And so I get this, which is the answer. Part C says use the change of basis matrix we found in part A and the answer we just found for part B to compute the coordinates of W relative to B primed. And okay, the answer to that is just you take the coordinates of B and take your change of basis matrix and multiply them. That was essentially the definition of change of basis matrix. It changed the coordinates of a vector in B to the coordinates of a vector in B primed. So we get this. Part D says check your work by computing the coordinates of B prime directly. And so this is similar to part B here. Well, so then we just multiply B primed inverse and W, and that will be the coordinates of W relative to B primed. And here's the Sage code for that, and we get the same answer as we found earlier.